What do you think the next big discovery will be? Story 1: Silicon has been the backbone of the computing revolution for over 60 years, but it's running into genuine physical limits that no amount of clever engineering can fully overcome. Transistors have been shrunk to the point where quantum tunneling effects, electrons leaking through barriers they shouldn't classically be able to cross, start interfering with reliable switching behavior at the smallest current process nodes, somewhere around 2-3 nanometers. Moore's law, the decades-long observation that transistor density roughly doubles every 2 years, has been visibly slowing for the better part of a decade, and most serious people in the semiconductor industry no longer expect silicon scaling to deliver the same kind of exponential improvement it has historically. The candidates being seriously researched as potential successors are genuinely diverse. Gallium nitride and silicon carbide are already in limited commercial use for power electronics, offering better performance at high voltages and temperatures. Carbon nanotube transistors have demonstrated theoretical performance advantages in lab settings, but face brutal manufacturing consistency challenges at scale. Two-dimensional materials like graphene and molybdenum disulfide offer atomically thin channel layers that could enable transistors smaller than silicon physically allows. Photonic computing, which uses light rather than electrical current to process information, sidesteps some of silicon's fundamental limitations entirely, but requires a complete rethink of chip architecture. Battery technology sits in a similarly overdue position. Lithium-ion batteries have improved incrementally for decades, but remain fundamentally limited by the chemistry of intercalation. Lithium ions inserting themselves into electrode material, which caps energy density at levels well below what solid-state batteries, lithium-sulfur chemistries, or other next-generation approaches theoretically promise. Solid-state battery development specifically has attracted billions in investment from major automakers and battery manufacturers, all racing toward a breakthrough that could double energy density while eliminating the fire risk associated with liquid electrolytes. Whichever breakthrough arrives first, the world is overdue for both, and the company or research group that cracks either one first stands to reshape entire industries. Story 2: Fusion energy and particle physics discoveries occupy a similar psychological space in the public imagination. Both have been on the verge for so long that the anticipation itself has become a recurring cultural joke, and both are, somewhat paradoxically, also genuinely closer to delivering something significant than that joke usually credits. On the fusion side, the National Ignition Facility's December 2022 demonstration of fusion ignition, producing more energy from the fusion reaction than the laser energy used to trigger it, was a genuine scientific milestone, even though it remains far short of the energy output required for a viable power plant. Private companies including Commonwealth Fusion Systems and Helion Energy are pursuing compact tokamak and other reactor designs with commercial timelines measured in years rather than the multi-decade horizons that characterize government-led fusion research for most of its history. On the particle physics side, the Large Hadron Collider's confirmed discovery of the Higgs boson in 2012 completed the Standard Model's core predictions, but it also left physicists with a frustrating absence of any clear signal pointing toward what comes next. Supersymmetry, extra dimensions, and various other theoretical extensions to the Standard Model have all been searched for at the LHC without confirmed detection, which has left the field in a genuinely uncertain position. Either the next significant discovery requires higher collision energies than the LHC can currently produce, suggesting the need for an even larger future collider, or it requires looking in places nobody has thought to look yet. What makes both fields perpetually exciting, despite the repeated false starts, is that the stakes of an actual breakthrough are proportionally enormous. Fusion would solve the energy and climate problems simultaneously, and a genuine particle physics discovery beyond the Standard Model would represent the first crack in our fundamental understanding of matter in over 50 years. Story 3: The case for artificial general intelligence, AI with human-level or greater capability across essentially any cognitive task, rather than narrow competence in specific domains. Being the next big discovery is harder to dismiss than it would have been even 5 years ago, precisely because large language models have repeatedly demonstrated capability jumps as they scale that weren't explicitly programmed in and weren't always anticipated by their own developers. What makes this prediction genuinely interesting rather than purely speculative is the trajectory of capability emergence. Early language models struggled with basic reasoning tasks. Successive generations have demonstrated increasingly sophisticated performance on standardized tests, coding tasks, and multi-step reasoning problems, sometimes crossing capability thresholds that researchers hadn't specifically trained for, in a pattern some researchers describe as emergent capability. Skills that appear somewhat suddenly once a model crosses a certain scale threshold, rather than improving smoothly and predictably alongside scale. The debate among AI researchers about how close we actually are to something resembling strong or general AI remains genuinely unresolved, with serious, credentialed researchers landing in meaningfully different places. Some argue current transformer-based architectures, however impressive, are fundamentally limited and will hit diminishing returns from further scaling, requiring genuinely new architectural approaches before anything resembling general intelligence becomes achievable. Others argue the trajectory of the past several years suggests we may already be closer to the threshold than most public discourse credits, and that the remaining gap is more about engineering refinement, training methodology, and computational scale than about needing some currently missing conceptual breakthrough. What's genuinely notable is that this entry, strong AI happening anytime now, appears, in one form or another, across multiple separate responses on this exact thread, suggesting that whatever the technical reality, the cultural sense that something significant in AI capability is imminent has become remarkably widespread across people with very different starting assumptions about technology. Generally, story for this entry is distinct from most others on this list because it's not really asking for a single discrete scientific breakthrough, so much as hoping for a coordinated set of solutions to a genuinely converging set of pressures: global population growth, climate change reducing agricultural productivity in many regions, aquifer depletion accelerating in major food-producing areas, and increasing water stress affecting an estimated 2/3 of the world's population at least part of the year already. The technological pieces that could meaningfully address this are genuinely diverse and already in various stages of development. Desalination technology has improved substantially in energy efficiency over the past 2 decades, with reverse osmosis costs falling considerably, though the energy requirements remain significant and the brine waste byproduct poses its own environmental challenges that aren't fully solved. Precision agriculture, using sensor networks, satellite data, and AI-driven analysis to optimize water and fertilizer use down to the level of individual plants or small plots, has demonstrated significant water savings in pilot deployments without sacrificing yield. Genetically engineered drought-resistant and heat-resistant crop varieties are advancing, particularly for staple grains that feed the largest populations. Vertical farming and controlled environment agriculture offer a more radical reimagining, growing food in stacked, climate-controlled indoor facilities that use a small fraction of the water and land that conventional agriculture requires, though current costs remain prohibitively high for most staple crops, and the approach works best for high-value leafy greens rather than calorie-dense grains. What makes this entry feel less like science fiction and more like an urgent engineering and policy challenge is that none of these technologies require a conceptual breakthrough we don't already understand. They require scaling, cost reduction, and political will applied fast enough to outrun the converging pressures driving the crisis in the first place. Story 5, reversing aging and growing replacement organs, are often discussed together, and it's worth noting they're actually 2 distinct research programs that happen to share some underlying biological tools, both of which have moved considerably further from speculation into demonstrated laboratory and early clinical reality than most people realize. Organ regeneration from a patient's own tissue avoiding the rejection risk and donor shortage that plague conventional transplantation, has already produced working results for simpler tissue types. Bladders grown from a patient's own cells have been successfully implanted in human patients for over a decade. In research led by Anthony Atala's team at Wake Forest, tissue-engineered skin, cartilage, and tracheal segments have similarly moved from research to limited clinical application. The harder challenge is complex, vascularized solid organs, kidneys, livers, hearts, which require not just the right cell types, but a functioning internal blood vessel network capable of keeping the entire structure alive, a problem that's proven considerably more difficult than growing simpler tissue. 3D bioprinting, which deposits living cells in precise patterns layer by layer, is the technology most actively being developed to solve the vascularization problem, and researchers have demonstrated bioprinted tissue with rudimentary internal vessel networks, though a fully functional, transplantable bioprinted kidney or liver remains a goal rather than an achieved reality. The aging reversal side draws on related but distinct research, particularly partial cellular reprogramming, which has demonstrated the ability to reverse certain age-related cellular markers in animal models without erasing the cell's specific identity. Combining genuinely functional lab-grown organs with genuinely effective cellular age reversal would represent two of the most significant medical achievements in human history, and the underlying research programs for both, while incomplete, are real, funded, and actively producing incremental progress rather than sitting purely in the speculative category. Story 6. This prediction stands out on this list for being less speculative than most, since the trajectory it describes is already substantially underway and has been for several years, making this less a forecast about an unknown future breakthrough and more an extrapolation of an existing, observable trend. SpaceX's reusable Falcon 9 rocket has already reduced launch costs by roughly an order of magnitude compared to the expendable rockets that preceded it, and the company has flown private astronaut crews on complete orbital missions, alongside routine crewed missions to the International Space Station through NASA's Commercial Crew Program. Blue Origin and Virgin Galactic have both flown paying customers on suborbital flights, crossing the threshold of ordinary wealthy people, not just government astronauts, can buy a ticket to space years ago rather than this remaining purely theoretical. The 10-year prediction for multiple companies running commercial space operations is, if anything, a fairly conservative restatement of where the industry already stands. Multiple companies are already operating, competing, and in some cases turning a profit on specific segments of the launch and tourism market. The 50-year prediction for broad affordability is the more genuinely speculative part of this forecast, and it hinges substantially on whether SpaceX's Starship program, designed for full and rapid reusability at a much larger scale than Falcon 9, can deliver the dramatic further cost reductions the company has stated as its explicit goal. Cost reduction in spaceflight has historically tracked closely with reusability and flight frequency. The more a vehicle flies, the more its fixed development costs get amortized across each flight, and the more operational experience drives down per-flight costs through accumulated efficiency improvements. Whether most people can afford it within 50 years specifically comes true depends on costs falling by roughly another order of magnitude or more beyond where they sit today, which is an aggressive, but not obviously impossible trajectory given the pace of the last 15 years alone. Story 7. Geothermal energy itself isn't new. Power plants have operated in volcanically active regions like Iceland and parts of the western United States for decades, drawing on naturally occurring underground heat sources close enough to the surface to be economically accessible with conventional drilling. The limitation has always been geographic. Most of the world simply doesn't sit on the kind of naturally occurring hydrothermal resources that conventional geothermal technology requires. What's changed the calculus and made economical geothermal feel like a genuinely achievable near-term discovery rather than a permanent limitation is the development of enhanced geothermal systems, which borrow drilling and reservoir engineering techniques directly from the oil and gas industry to access the Earth's heat at locations and depths that don't have naturally occurring hydrothermal resources. The approach involves drilling deep wells into hot rock, creating an engineered network of fractures, and circulating water through that network to extract heat that would otherwise be commercially inaccessible. The breakthrough that's actually moving this from theoretical to commercially viable is drilling technology itself. Companies including Quaise Energy are developing millimeter wave drilling technology, borrowed from Fusion Research's plasma heating systems, that can vaporize rock at depths and speeds far beyond what conventional mechanical drill bits achieve, potentially reaching the extreme depths required for supercritical geothermal resources. Heat sources hot enough to make the technology viable virtually anywhere on the planet, not just in geologically fortunate locations. If drilling costs fall enough to make enhanced and supercritical geothermal economically competitive with other energy sources, the resource itself is effectively limitless on any human timescale and available beneath nearly every populated region on Earth, which would make it one of the cleanest possible solutions to the energy and climate problem, precisely because it doesn't face the intermittency challenges that solar and wind power do. Story 8. This entry takes a sharp, deliberately unsettling turn away from the optimistic technological predictions filling most of this list, and it's worth treating seriously as a thought experiment, precisely because it engages with a genuinely under-discussed category of risk in the search for extraterrestrial intelligence. The scenario being proposed draws on a real category of theoretical concern that SETI researchers and astrobiologists have actually debated seriously: the risk that any signal received from an alien civilization might not simply be passive information to be studied, but could potentially function as something closer to a digital payload, designed, whether maliciously or simply as a natural consequence of its informational structure, to replicate itself once received and processed by sufficiently advanced computing infrastructure, similar in principle to how a biological virus hijacks a host cell's own machinery to reproduce itself. This concern has actually informed real policy discussions within the SETI community about message construction and response protocols. Some researchers have argued for caution specifically around actively transmitting messages into space, a lactus called active SETI, precisely because we have no way of predicting how a sufficiently advanced or sufficiently different intelligence might respond. And others have raised the theoretically parallel concern about what we might be vulnerable to if we received rather than sent first. The specific mechanism proposed in this entry, a signal that copies itself onto storage media and somehow retrofits the entire planet into a device for further propagation, extends considerably beyond what current SETI risk discussions typically consider, venturing into territory closer to science fiction, exploring posthuman or non-biological intelligence and self-replicating technology. Neumann probes being the most commonly discussed real theoretical version of self, replicating space-faring technology than into documented current astrobiological risk assessment. But the underlying instinct, that first contact via received signal, carries genuine uncertainty and potential danger we haven't fully reasoned through, is a real and seriously held position within the field, not purely speculative anxiety. Story 9. Wireless power transfer sounds like a futuristic prediction, but it's worth noting that a limited version of exactly this technology already exists and is in widespread consumer use, which makes this entry less a speculative forecast and more a question of how far an existing working technology can be scaled. Inductive charging, using the same basic electromagnetic principle Nikola Tesla experimented with over a century ago, already powers wireless phone chargers, electric toothbrushes, and certain electric vehicle charging pads, transmitting power across small air gaps using oscillating magnetic fields that induce current in a receiving coil. The fundamental physics works and is commercially deployed. What's limited is range and efficiency. Current consumer wireless charging requires the device to be placed in very close proximity, typically touching or nearly touching the charging pad, with efficiency dropping off sharply as distance increases. The genuinely speculative, larger-scale version of this prediction, wirelessly powering devices across a room or transmitting meaningful amounts of power across longer distances entirely without wires, faces more significant physics and safety challenges. Resonant inductive coupling, which tunes both transmitter and receiver to the same resonant frequency, has demonstrated improved range over basic inductive charging in research settings, with some systems achieving meaningful power transfer across a few meters. Microwave and laser-based power transmission, which can theoretically transmit power across much longer distances, including potentially from orbit to the ground, face significant beam safety and efficiency challenges that have kept them largely in the research and niche application category. Space-based solar power transmitted to Earth via microwave beam has been seriously studied by several space agencies, but remains technically and economically unproven at scale. The next big discovery here likely isn't a fundamentally new physical principle, since the principles are already well understood. It's an efficiency and range breakthrough that makes room-scale or building-scale wireless power genuinely practical rather than a niche curiosity. Story 10 carbon nanotubes have been a fixture of materials of the future discussions for over 2 decades, and the gap between their demonstrated laboratory properties and their actual commercial deployment is a genuinely interesting case study in how a discovery can be simultaneously well understood and stubbornly difficult to scale. The individual properties of carbon nanotubes are, on paper, extraordinary. Their tensile strength to weight ratio dramatically exceeds steel. Their electrical conductivity rivals copper at a fraction of the weight, and their thermal conductivity exceeds most known materials. These properties have made carbon nanotubes a proposed solution to an enormous range of separate engineering challenges. The cable material required for a space elevator, lighter and stronger composite materials for aerospace and automotive applications, more efficient electrical interconnects for computing, and improved battery electrode materials, among many others. The persistent bottleneck has never really been discovering carbon nanotubes' properties that happened decades ago, but manufacturing them consistently, at length, and at the volumes industrial applications would require. Producing individual carbon nanotube fibers with research-grade properties is achievable in small laboratory quantities. Producing them with consistent quality at the macroscopic lengths and industrial volumes that practical applications need has proven to be a much harder materials engineering and manufacturing process challenge, one that's resisted solution for considerably longer than early optimistic predictions from the early 2000s anticipated. Several companies and research groups continue pursuing improved chemical vapor deposition techniques and other manufacturing approaches aimed specifically at this scaling problem, and incremental progress has been made in producing longer, more consistent nanotube fibers and yarns. A genuine breakthrough in mass production. Manufacturing nanotubes at industrial scale with properties close to their laboratory potential would unlock numerous already designed but currently impractical applications simultaneously, making it one of the rare bottleneck technologies where solving one manufacturing problem cascades into progress across an unusually wide range of separate fields. Story 11 of all the predictions on this list. This is the one whose significance requires the least justification. Confirmed evidence of life beyond Earth, even simple microbial life, would be one of the most consequential scientific discoveries in human history, fundamentally altering our understanding of how common or rare biology actually is in the universe. The search has several genuinely promising near-term avenues currently active. Mars remains the most accessible candidate, with NASA's Perseverance rover currently collecting samples specifically selected from an ancient river delta environment in Jezero Crater, chosen because it represents exactly the kind of setting where ancient microbial life, if it ever existed, would most plausibly have left detectable traces. Those samples are intended for eventual return to Earth, where laboratory analysis far more sensitive than anything deployable on the Martian surface itself can examine them properly for biosignatures. The icy moons of the outer solar system represent a different and in some ways more promising category of target. Europa, orbiting Jupiter, and Enceladus, orbiting Saturn. Both show strong evidence of liquid water oceans beneath their icy surfaces, kept liquid by tidal heating from their respective host planets' gravity. Enceladus specifically has been observed venting water plumes from its south pole that spacecraft have already flown through and sampled, finding organic molecules and chemical conditions consistent with, though not proof of, the kind of environment that could support microbial life. Beyond our own solar system, the James Webb Space Telescope is actively analyzing the atmospheric composition of select exoplanets for biosignature gases, combinations of atmospheric chemicals that are difficult to explain through purely geological or chemical processes without biological activity. A confirmed detection here wouldn't provide a photograph of an alien organism, but a sufficiently compelling biosignature spectrum would shift scientific consensus dramatically, possibly within the next decade, rather than requiring a much longer wait. Story 12, transmuting one element into another, sounds like it belongs purely to medieval alchemy rather than modern science, but the underlying physics is genuinely well established and has been demonstrated, just not yet at anything resembling industrial scale or economic viability, which is exactly the gap this prediction is betting will eventually close. Nuclear transmutation, changing one element into another by altering the number of protons in its nucleus, happens constantly in nature through radioactive decay and has been deliberately achieved by humans since the early 20th century through particle bombardment and nuclear reactions. Ernest Rutherford achieved the first deliberate artificial transmutation in 1919, converting nitrogen into oxygen through alpha particle bombardment. Nuclear reactors and particle accelerators have since been used to deliberately produce specific isotopes and elements for medical, research, and even precious metal production purposes. Gold has actually been produced from other elements through nuclear reactions, though it costs many orders of magnitude higher than simply mining gold conventionally, making it a scientific curiosity rather than an economically meaningful process. What industrial scale would actually require is a method of inducing controlled nuclear transmutation efficiently enough and cheaply enough to be economically competitive with conventional resource extraction, mining, or chemical synthesis for the specific applications involved. This is a genuinely enormous engineering challenge, since nuclear reactions generally require far more energy input than chemical reactions to initiate and control. And the byproducts of nuclear transmutation processes can include genuinely hazardous radioactive material requiring careful handling and disposal. The most plausible near-term application isn't producing valuable elements like gold, but rather nuclear waste remediation, transmuting long-lived, highly radioactive waste isotopes into shorter-lived or stable isotopes, dramatically reducing the storage timeline challenges associated with conventional nuclear waste. Several research programs are actively pursuing exactly this application, which would represent a genuinely valuable industrial-scale transmutation breakthrough, even if it's a less dramatic application than alchemical gold production. Story 13, this entry is notably more personal and grounded than most of the others on this list, and it deserves to be treated as a genuinely reasonable medical research wish rather than dismissed as a minor or self-interested ask, because cognitive enhancement specifically targeting memory, without relying on stimulants that carry their own side effect profile and questionable efficacy for the specific problem of memory consolidation, is an active, serious area of neuroscience research. Current ADHD medications, predominantly stimulants like methylphenidate and various amphetamine formulations, work primarily by increasing dopamine and norepinephrine activity in the brain, which improves attention and executive function for many people, but doesn't directly or reliably address memory formation and retrieval as a distinct cognitive process. The frustration expressed here that stimulants don't really solve the specific memory problem reflects a genuine gap in current pharmacology between attention-focused and memory-focused cognitive enhancement, which are related but distinct neural processes. Research into genuinely memory-targeted interventions has explored several different mechanisms. Ampakines, a class of compounds that enhance signaling at AMPA receptors involved in synaptic plasticity, have shown some promise in animal studies and limited human trials for improving memory consolidation, though none have yet reached widespread clinical availability for this specific purpose. Research into the molecular mechanisms of long-term potentiation, the cellular process underlying memory formation, has identified numerous potential drug targets, including compounds affecting CREB protein signaling, which plays a documented role in converting short-term memories into long-term ones. Non-pharmacological approaches are advancing in parallel, including targeted transcranial magnetic or electrical stimulation protocols that have shown some ability to enhance memory consolidation, particularly during sleep, when memory consolidation processes are naturally most active. Closed-loop stimulation systems, which monitor brain activity in real time and deliver stimulation precisely timed to enhance naturally occurring memory consolidation processes, represent a particularly promising and active research direction. A genuine, reliable, side-effect light memory enhancer would have enormous appeal well beyond people managing attention difficulties specifically, which is exactly why this remains such an active area of pharmaceutical and neurotechnology research investment. Story 14, this entry, takes the form of a genuinely vivid, almost narrative thought experiment rather than a straightforward prediction, and it's worth unpacking the specific claims embedded in it, because they touch on real, active areas of neuroscience and philosophy of mind. Even though the dramatic conclusion, humanity collectively shrugging off existential uncertainty and setting out to colonize the universe, is speculative fiction rather than scientific forecast. The premise of accidentally discovering a way to shift human cognition toward a mode less dependent on petty emotions draws on real research into the relationship between emotional processing and higher-order reasoning. Neuroscience has increasingly moved away from the older, simpler model that treated emotion and rationality as opposing forces, toward a more integrated understanding in which emotional processing is actually foundational to effective decision-making, not merely an obstacle to it. Patients with damage to brain regions involved in emotional processing, such as certain frontal lobe injuries, often show impaired rather than improved practical decision-making, despite intact logical reasoning capacity, a finding that significantly complicates any simple remove the emotions, gain pure rationality narrative. This doesn't mean the broader concept of altering or expanding modes of cognition is purely fantastical. Meditation research has documented measurable changes in brain activity and structure associated with long-term contemplative practice, including changes in emotional regulation and self-referential thought processing. Certain psychedelic compounds, now being seriously researched again after decades of prohibition-driven research stagnation, produce measurable shifts in brain connectivity patterns, particularly affecting the default mode network associated with self-referential thinking, and users frequently report exactly the kind of shift toward perceived higher order or less ego-bound thinking this entry describes. What this entry actually captures well, even through its speculative framing, is a genuine and serious open question in neuroscience and philosophy, whether human cognition as currently configured represents some kind of optimal or fixed endpoint, or whether meaningfully different, perhaps genuinely higher modes of cognitive processing remain accessible through interventions we haven't yet fully developed or understood. Story 15, this entry, stands apart from nearly everything else on this list, because it's not proposing a technological or scientific discovery at all. It's proposing a kind of inward, cultural or psychological rediscovery, framed deliberately in the same language as the other entries, to suggest that the most significant discovery still ahead of us might not be something we build, but something we recover. The underlying concern being gestured at here has genuine support in contemporary research on attention, well-being, and technology use. Studies on smartphone and social media use have documented measurable associations with reduced attention span, increased anxiety and depressive symptoms in some populations, particularly adolescents, and disrupted sleep patterns, though the research in this area remains genuinely contested regarding causation, magnitude, and which specific usage patterns are actually responsible for which specific effects, rather than being as settled and alarming as some popular accounts suggest. What does have more solid research backing is the broader concept of attention restoration and the cognitive cost of constant digital stimulation and interruption. Research on continuous partial attention, the state of perpetually monitoring multiple streams of information and notification rather than engaging deeply with any single task, has documented measurable impairments in working memory performance and task completion quality compared to periods of focused, uninterrupted attention. The broader cultural conversation around digital minimalism, intentional technology use, and structured periods of disconnection draws directly on this research, proposing that meaningful psychological and cognitive benefits are available simply by deliberately reducing the kind of constant stimulation modern entertainment and communication technology defaults to providing. This entry's framing, treating personal and cultural recovery of attention, presence, and depth as a discovery on par with technological breakthroughs, is a genuinely interesting reversal of the assumption embedded in most of the rest of this list, that progress necessarily means adding something new, rather than potentially involving the rediscovery of capacities that previous, less technologically saturated generations simply had by default, without needing to consciously cultivate them. Story 16, colonizing the moon's craters, the specific, practical version of lunar settlement. This entry's specificity, craters specifically, rather than lunar settlement generally, is worth taking seriously, because it correctly identifies the actual, most scientifically credible target location for early lunar settlement, rather than the more generic humans on the moon framing that popular discussion often defaults to. The specific craters relevant here are the permanently shadowed craters located at the moon's south pole, regions that never receive direct sunlight due to the moon's minimal axial tilt and the specific topography of the polar region. These permanently shadowed areas are extraordinarily cold, cold enough that volatile compounds, including water ice, can persist there for potentially billions of years without sublimating away, unlike most of the lunar surface, which experiences temperature swings extreme enough to make water ice retention impossible over long timescales. Confirmed detection of water ice in these specific polar craters, established through orbital data from multiple missions and directly confirmed on the ground by India's Chandrayaan-3 mission landing in the South Polar region in 2023, has made this exact location the focal point of essentially every serious current lunar settlement plan, including NASA's Artemis program and China's parallel lunar ambitions. Water ice means drinking water, breathable oxygen through electrolysis, and potentially the hydrogen and oxygen components needed for rocket fuel. Exactly the resources required to make a lunar settlement genuinely self-sustaining, rather than entirely dependent on continuous, expensive resupply missions from Earth. The engineering challenge specific to these crater locations is also genuinely interesting, building habitats and solar power infrastructure that can operate near permanently shadowed, extremely cold regions while still accessing nearby areas with sufficient sunlight for power generation, since the same polar geography that keeps the crater floors permanently dark also creates nearby peaks of eternal light, elevated terrain that receives near continuous sunlight, offering an unusually favorable power generation opportunity right next to the resource-rich shadowed craters. Story 17, supermagnets and the 15-20-year promise, a genuinely confident, specific bet. What makes this entry distinctive on the list is its specificity and confidence, rather than a vague gesture toward magnet technology. The prediction commits to a time frame and a stated willingness to personally deliver on it, which is worth examining against what's actually happening in material science. Research into magnetic materials right now. Advanced permanent magnets, particularly rare earth magnets using neodymium and related elements, already underpin an enormous range of current technology. Electric vehicle motors, wind turbine generators, hard disk drives, and emery machines, among many others. The genuine bottleneck and active research frontier isn't whether strong magnets exist, since neodymium magnets are already remarkably powerful for their size, but rather supply chain vulnerability. Rare earth elements are geographically concentrated in extraction and refining, creating genuine strategic and economic risk, and the search for comparably powerful magnetic materials that don't depend on rare earth elements at all. Iron nitride magnets have attracted serious research attention as a potential rare earth-free alternative, with some research suggesting theoretical magnetic performance that could rival or exceed current rare earth magnets. Though manufacturing iron nitride magnets with consistent, scalable quality has proven to be a genuinely difficult materials science and manufacturing challenge that's kept the technology in the research and pilot production stage rather than widespread commercial deployment. Superconducting magnets represent an entirely different and arguably more transformative category, since superconductors carry current with zero electrical resistance, enabling magnetic field strengths far beyond what conventional or even rare earth permanent magnets can achieve. High-temperature superconducting magnets have already enabled the compact, powerful magnetic confinement systems, driving some of the most promising current fusion reactor designs and continued materials science progress toward higher temperature. More practical superconductors would meaningfully accelerate fusion development, medical imaging technology, and high-speed maglev transportation simultaneously. The 15-20 year window proposed here is a genuinely plausible time frame for meaningful progress on at least one of these fronts, even if which specific magnetic technology breakthrough actually arrives first remains an open question. Story 18: Digitally Mediated Telepathy. The beak eye prediction, with a pointed joke about who gets it first. This entry's core technical prediction, that reliable, non-invasive brain-computer interface technology will eventually enable direct thought sharing between people, is grounded in genuinely active and rapidly advancing research. Even though the specific joke about military technology eventually trickling down to public release deserves its own separate examination, current brain-computer interface research is split between invasive approaches, which requires surgical implantation directly into or onto brain tissue neural, and synchron being the most prominent current examples, and non-invasive approaches, which read brain activity from outside the skull, using technology like EEG, electrical activity, or FNIRS, detecting blood oxygenation changes associated with neural activity. Invasive approaches currently offer dramatically higher signal resolution and have already enabled paralyzed patients to control computer cursors and communicate at meaningful speeds. Non-invasive approaches remain considerably more limited in resolution and reliability, which is exactly the bottleneck this entry correctly identifies as the key obstacle to broader voluntary public adoption. Most people are unlikely to choose brain surgery for a non-medical enhancement, no matter how compelling the capability, which makes a genuine, non-invasive break through the more realistic pathway to mass-market thought interface technology. Genuine thought sharing between two people specifically, as opposed to one person controlling an external device, would require not just reading neural signals reliably, but also writing or inducing comparable neural patterns in a receiving brain, a considerably more complex bidirectional problem than current BCI research, which is overwhelmingly focused on the reading direction alone, has yet seriously attempted to solve at the level of complex thought content rather than simple sensory stimulation. The joke about military development preceding public release does have real historical precedent. GPS, the Internet's foundational ARPANET infrastructure, and significant portions of modern prosthetics and robotics technology all originated substantially through military-funded research, including DARPA specifically, before subsequent civilian and commercial adaptation, which gives this particular joke more grounding in actual technology history than pure cynicism alone would provide. Story 19: Negligible Senescence for Humans. The aging research wish with real animal precedent negligible senescence is an actual, specific scientific term, not a phrase invented for this entry. It describes organisms that show no measurable increase in mortality rate or decline in reproductive capacity with age. Essentially, organisms that don't age in the way most species do. And several real species genuinely fit this description, giving the human aspiration expressed here a concrete biological precedent to point toward. Certain rockfish species, some turtle species, and the famous immortal jellyfish Turritopsis dohrnii, capable of reverting to an earlier developmental stage when stressed, effectively restarting its life cycle indefinitely, all demonstrate that negligible senescence is biologically achievable, at least in specific organisms with specific biological architecture. Which removes negligible senescence is theoretically impossible from the table as a counterargument, even though achieving it in a creature as biologically complex as a human remains a vastly harder engineering and biological challenge. Current human aging research, organized increasingly around the hallmarks of aging framework, identifies roughly 9 or 10 distinct biological mechanisms driving age-related decline: cellular senescence, telomere attrition, mitochondrial dysfunction, and several others, each independently addressable, at least in principle, with current or near-term biotechnology. Senolytic compounds that clear senescent zombie cells have demonstrated genuine lifespan and health span extension in animal models. Partial cellular reprogramming research has shown promising results reversing certain age-related cellular markers without erasing cell identity. The cancer tablets aside in this entry, while seemingly tangential, actually connects to the aging research directly. Cancer risk and cellular senescence are deeply biologically intertwined, since many of the cellular mechanisms that prevent uncontrolled cell division, poor feature of vision, also drive the accumulation of senescent cells associated with aging, meaning genuine progress on either problem frequently has direct relevance to the other. A treatment that could reliably address cellular senescence without increasing cancer risk would represent meaningful progress on both fronts simultaneously, which is exactly why so much current longevity research treats these as overlapping rather than separate problems. Story 20 accurate lie detectors and detailed brain scans, a wish with serious ethical stakes attached. This entry pairs two related but distinct technologies, and it's worth examining both separately, because the gap between current capability and what's being wished for here is genuinely significant, and the ethical implications of actually closing that gap are considerably more complicated than the simple "wouldn't that be useful" framing might initially suggest. Current polygraph lie detection technology, despite its widespread cultural recognition and historical use in law enforcement and security screening, is not considered scientifically reliable by the overwhelming consensus of psychological and forensic science research. Polygraphs measure physiological arousal, heart rate, skin conductance, breathing patterns, which correlates with stress and anxiety generally, not specifically and exclusively with deception, meaning a genuinely nervous truth teller and a calm, practiced liar can both produce misleading results. This unreliability is well documented enough that polygraph results are generally inadmissible as primary evidence in American courts. More advanced neuroimaging-based approaches to lie detection, using fMRI to observe brain activity patterns associated with deception, have shown somewhat more promising results in controlled laboratory research settings, detecting specific patterns of prefrontal cortex activity associated with the cognitive effort of constructing a lie versus retrieving a true memory. However, these approaches remain expensive, require large immobile scanning equipment entirely impractical for routine use, and have not been validated for reliability outside of tightly controlled laboratory conditions in ways that would make them defensible for real-world legal or security applications. The genuine breakthrough this entry is hoping for: reliable, practical, real-world lie detection combined with detailed, accessible brain scanning would represent a profound shift in surveillance and privacy capability, well beyond its obvious appeal for criminal justice and security applications. The same technology that could reliably catch criminals lying could equally be used coercively against political dissidents, employees, or anyone subjected to it without genuine consent, which is exactly why bioethicists who study this technology's trajectory tend to discuss it with considerably more caution than straightforward enthusiasm. Story 21, Freeze, Raise, and Stop Time. The joke entry that's doing real comedic work. This entry is delivered as pure, deadpan comedy, and it's worth appreciating it specifically as comedy, rather than attempting to force a serious scientific reading onto something that's clearly, intentionally absurd. A brief callback to the genre of over-the-top. Self-aware joke entries that appear periodically across lists like this one as a kind of structural palate cleanser between earnest predictions. The freeze ray reference draws on a long science fiction and cartoon tradition of weapons that instantly freeze their target solid, a trope with no basis in actual physics. Instantly lowering an object's temperature to freezing point would require near instantaneous removal of an enormous amount of thermal energy, a process that, even with hypothetical future technology, would likely require either an extraordinarily fast and energy-intensive cooling mechanism or some entirely speculative physical principle with no current theoretical basis whatsoever. Stop Time pushes the joke even further into the territory of physical impossibility as currently understood, since time, within general relativity, isn't a uniform background that something could simply pause or halt. It's a dimension woven together with space into space-time itself, and stopping it for a localized region while everything else continues isn't merely difficult. It's not a coherent concept within any current physical framework. Fictional energy shields and convenient narrative pauses notwithstanding. The deadpan tell your friends closing line is the entry doing exactly what it's supposed to do, presenting two genuinely impossible technologies with the same flat, matter-of-fact confidence as the earnest, well-reasoned scientific predictions surrounding it elsewhere on this list, producing a small but genuine comedic payoff specifically from that tonal mismatch. Lists built from open community submissions reliably produce at least one entry like this, and its value isn't scientific at all. It's a reminder that not every contribution to a thread like this is meant to be taken at face value, and the best ones land their joke with total commitment rather than winking at the reader. Story 22, Manipulating Electron Spin. The Quantum Frontier, a new account was created just to mention. There's something genuinely endearing about an entry that opens by noting the person made an account specifically to contribute this one idea, and the idea itself, that manipulating electron spin states represents the next major frontier, beyond our current largely charge-based electronics and chemistry, is grounded in real, actively developing physics rather than vague futurism. Conventional electronics and most current chemistry-based technology work primarily by manipulating electron charge, the flow of electrons carrying electrical current, or the sharing and transfer of electrons in chemical bonding. Electron spin, a quantum mechanical property roughly analogous to, but not literally, a tiny rotating magnetic moment associated with each electron, has historically been a secondary consideration in most practical technology, even though it's been understood theoretically since the early 20th century, and is fundamental to phenomena like magnetism. Spintronics, the field specifically focused on exploiting electron spin rather than just charge for information processing and storage, has already produced real commercial technology. The read heads in modern hard disk drives use giant magnetoresistance, a spin-dependent effect, and this discovery was significant enough to win its discoverers the 2007 Nobel Prize in Physics. The next frontier the entry is gesturing toward involves more sophisticated spin manipulation for computing applications specifically, including spin-based quantum computing approaches that use electron spin states as qubits, and neuromorphic spintronic memory designs discussed elsewhere on this exact list that could dramatically reduce the energy cost of moving data between memory and processing units, a major bottleneck in current computer architecture. Quantum computing more broadly, which manipulates quantum properties including, but not limited to electron spin to perform certain calculations in fundamentally different ways than classical computers, has moved from purely theoretical physics to genuine, if still early stage, working hardware over the past decade. Making manipulating electron spin is going to pave the way for some wicked cool science, a genuinely well-aimed prediction, even delivered in considerably more casual language than most physics forecasts. Story 23, liquid-like electron transitions. When electrons stop acting like particles or crystals and start flowing, this entry describes a genuinely cutting-edge and somewhat exotic area of condensed matter physics research. And it's worth unpacking carefully, because the underlying phenomenon represents a third behavioral category for electrons that doesn't map cleanly onto either of the two states most people learn about in basic physics education. Conventionally, electrons and materials are typically described in one of two ways depending on the material and conditions, as essentially independent particles moving relatively freely, as in conductive metals, or as locked into a rigid, ordered geometric arrangement called a Wigner crystal, a state predicted theoretically by Eugene Wigner in 1934, in which electrons, under specific conditions of low density and strong mutual repulsion, arrange themselves into a fixed crystalline lattice pattern, similar in spirit to how atoms arrange themselves in a conventional solid crystal, except the particles forming the lattice are the electrons themselves. What researchers are now identifying, primarily through careful experiments on specially engineered two-dimensional materials and heterostructures, is an intermediate electronic state where the Wigner crystal structure melts, not through simple heating in the conventional sense, but through specific quantum mechanical and density-dependent effects, into a state where electrons move collectively, behaving more like the coordinated, correlated flow of a liquid than either the rigid lattice structure of the crystal state or the largely independent motion of conventional metallic conduction. This matters beyond pure theoretical interest, because understanding and eventually controlling this liquid-like collective electron behavior could open up entirely new categories of electronic device behavior that don't map onto existing transistor-based computing architecture at all, potentially enabling new forms of highly efficient information processing or sensing that exploit collective quantum effects rather than individual electron switching. This is squarely the kind of fundamental materials physics discovery that doesn't produce an immediately obvious consumer product, but that historically has been exactly the category of finding, like the original discovery of semiconductor behavior itself, that eventually underpins technology nobody could have specifically predicted from the initial physics alone. Story 24, exosome-targeted drug delivery. Hijacking the body's own mail system instead of building new trucks, this entry describes a genuinely clever reframing of the drug delivery problem in medicine. And it's worth understanding why using the body's own existing biological transport system represents a meaningfully different and potentially superior approach compared to the synthetic. Nanoparticle delivery systems that have dominated recent pharmaceutical innovation, mRNA vaccine lipid nanoparticles being the most prominent recent example. Exosomes are small vesicles, membrane-bound sacs, that essentially every cell in the human body naturally produces and releases, carrying proteins, genetic material, and other molecular cargo between cells as a normal part of cellular communication and signaling throughout the body. They're not a foreign or synthetic technology at all. They're a naturally occurring biological mail system that the body already uses constantly, which is exactly the property researchers are now trying to exploit for therapeutic drug delivery. The advantage of hijacking exosomes rather than building synthetic nanoparticle delivery vehicles from scratch is significant. Synthetic nanoparticles, however well engineered, are foreign material that the immune system can potentially recognize and attack, clearing them from the bloodstream before they reach their intended target, or triggering unwanted inflammatory responses. Exosomes, being entirely the body's own natural material, are far less likely to trigger this kind of immune clearance or adverse reaction, potentially allowing therapeutic payloads to reach target tissues more efficiently and with fewer side effects than synthetic delivery vehicles. Researchers are actively working on methods to load exosomes with specific therapeutic cargo, chemotherapy drugs, gene therapy components, or other treatments, and in some approaches, modifying the surface proteins on exosomes to specifically target particular cell types, such as cancer cells, with much greater precision than systemic drug administration typically achieves. This research remains in relatively early stages compared to established synthetic nanoparticle delivery, but the fundamental advantage of working with the body's own transport machinery rather than against potential immune recognition of foreign material makes this one of the more conceptually elegant directions in current targeted drug delivery research. Story 25: Anti-Friedel-Crafts reactions. The accidental discovery that broke a century-old chemistry rule, the Friedel-Crafts reaction, first described by Charles Friedel and James Crafts in 1877, is one of the foundational reactions taught in organic chemistry, used to attach alkyl or acyl groups onto aromatic rings, structures, based on benzene like rings of carbon atoms using specific catalysts under specific conditions. For nearly a century and a half, this reaction has followed well-understood, predictable rules about which molecular positions get modified and under what conditions. Rules so foundational that they're embedded deeply into how chemists are taught to think about aromatic chemistry generally. What anti-Friedel-Crafts chemistry describes is the discovery of reaction pathways that systematically violate the expected selectivity rules of the classical Friedel-Crafts framework, producing products at molecular positions or under conditions that the century-old rules would have predicted to be unfavorable or simply not to occur. The genuinely striking part of this discovery, based on how it's described, is that it emerged accidentally. Researchers conducting what should have been routine, predictable chemistry observed unexpected products that didn't match what the well-established rules anticipated, and rather than dismissing the result as experimental error, pursued it carefully enough to identify a genuinely new reaction pathway. This matters considerably beyond pure academic interest, because Friedel-Crafts type reactions are used extensively in pharmaceutical synthesis, agrochemical production, and materials science. Anywhere aromatic ring systems need precise, controlled modification, a reliable method for achieving previously difficult or anti-selectivity patterns would open up synthetic routes to molecules that were previously difficult, expensive, or simply impossible to make efficiently using established methods, potentially accelerating development of new drug candidates or materials that require exactly the kind of unconventional molecular architecture this new reaction pathway can access. Accidental discoveries that overturn long accepted, foundational rules are relatively rare in a field as mature and well-studied as organic chemistry, which is precisely what makes this category of finding noteworthy. It's a reminder that even centuries-old, thoroughly textbook chemistry can still contain genuine surprises for researchers willing to take an unexpected result seriously, rather than assuming an error. Story 26: Passive radiative cooling materials, cooling below room temperature. Using zero electricity, this technology sounds like it should violate basic thermodynamics, which is exactly why it's worth explaining carefully. A material that cools itself below the surrounding ambient air temperature while sitting in direct sunlight, using no electricity or active cooling mechanism whatsoever, is genuinely real, demonstrated technology, not a thermodynamic impossibility, because it exploits a specific physics loophole most people never think about. The mechanism is called passive radiative cooling, and it works by exploiting a specific transparency window in Earth's atmosphere, a particular range of infrared wavelengths, roughly 8 to 13 micrometers, at which the atmosphere is unusually transparent, allowing thermal radiation at those specific wavelengths to pass essentially directly through to the cold vacuum of space, rather than being absorbed and re-radiated back down by atmospheric gases, the way most infrared radiation is. Every object on Earth's surface naturally radiates some thermal energy at these specific wavelengths constantly, but most materials don't do so efficiently enough relative to the heat they simultaneously absorb from sunlight and surrounding warm air to achieve net cooling. The breakthrough materials researchers have developed are specifically engineered to maximize emission at exactly this atmospheric transparency window, while simultaneously reflecting the vast majority of incoming visible sunlight, which would otherwise heat the material directly. By radiating heat efficiently into space through the atmospheric window, while reflecting away almost all incoming solar energy, these materials can achieve a genuine net cooling effect, dropping below ambient air temperature even while sitting in direct sunlight, entirely passively, using zero electrical input or active refrigeration cycle. The practical applications are substantial. Passive radiative cooling coatings or panels applied to building roofs and exterior walls could meaningfully reduce air conditioning energy demand in hot climates, addressing both energy costs and the broader strain that increasing global cooling demand places on electrical grids as climate change drives up average temperatures. Some early commercial deployments are already underway, particularly in warehouse and industrial building applications, with residential and broader infrastructure applications representing the next scaling frontier for the technology. Story 27 NAV 1.8 blockers, the painkiller that might finally separate pain relief from addiction, the fundamental problem with opioid painkillers, which remain the most powerful pain management tools currently available for severe pain, is that their pain-relieving mechanism and their addictive potential are deeply intertwined at the level of brain chemistry. Opioids work by activating receptors in the brain's reward and pain processing pathways simultaneously, which is precisely why they're so effective at pain relief, and precisely why they carry such severe addiction and overdose risk. A combination that has driven one of the most devastating public health crises in recent American history. NAV-1.8 sodium channel blockers represent a genuinely different therapeutic strategy that sidesteps this problem structurally, rather than trying to fine-tune around it. Sodium channels are proteins embedded in nerve cell membranes that are essential for transmitting pain signals from the site of injury or damage to the brain. When a sodium channel opens, it allows sodium ions to flow into the nerve cell, generating the electrical signal that propagates the pain message along the nerve. NAV-1.8 specifically is a particular subtype of sodium channel that's heavily concentrated in peripheral pain-sensing neurons specifically, rather than being broadly distributed throughout the central nervous system and brain reward pathways the way opioid receptors are. This anatomical specificity is the key advantage. A drug that selectively blocks NAV-1. 8 channels can interrupt pain signal transmission at the peripheral nerve level before the pain signal ever reaches the brain's central pain processing and reward circuitry, theoretically providing meaningful pain relief without ever directly engaging the brain reward pathways responsible for addiction in the first place. This is mechanistically a fundamentally different approach from opioids, which work by dampening the brain's response to pain signals that have already arrived, rather than blocking the pain signal's peripheral transmission before it gets there. Suzetrigine, a NAV-1.8 targeted non-opioid pain medication, received FDA approval in early 2025 for acute pain management, representing a genuinely significant milestone as one of the first new mechanistic approaches to pain management to reach market in decades, with researchers and physicians watching closely to see how broadly this approach can eventually be extended to other pain conditions beyond its initial approved use.